Right now, as you read this, the universe is conducting an experiment. It has been running this experiment for 13.8 billion years, without interruption, without pause, without any awareness that it is doing so at all. The experiment is simple in its design and staggering in its implications. It takes hydrogen, it waits, and it sees what hydrogen becomes. The answer in at least one case is you. You are the universe looking at itself. You are hydrogen that has spent billions of years collapsing into stars, burning, exploding, scattering, recollapsing, forming planets, cooling, pooling into oceans, assembling into molecules of extraordinary complexity, and eventually, inexplicably becoming aware, becoming curious, becoming the kind of thing that looks upward at night and wonders whether the same process has happened anywhere else. The mathematics say it should have. The mathematics say it almost certainly has. There are, by current conservative estimates, approximately 400 billion stars burning inside the Milky Way at this moment. Not 400 billion in total across all of history. 400 billion right now simultaneously pouring energy into the void at rates that dwarf anything the human mind was built to process. If you attempted to count them at a rate of 1 per second without sleeping, without pausing, the count would consume more than 1,200,000 years. You would begin counting before the last ice age ended. You would finish counting long after every civilization currently alive on Earth has risen and fallen and been forgotten. And that is only our galaxy. Beyond the Milky Way, the universe contains an estimated 2 trillion additional galaxies, 2 trillion collections of hundreds of billions of stars each. The total stellar population of the observable universe approaches a number so large that writing it out in standard notation would require more digits than there are atoms in the human brain. We have no intuitive language for quantities this vast. Our minds were shaped by evolution to track predators across savannas and count members of small social groups. The numbers of cosmology do not fit inside a human skull. They can only be pointed at, gestured toward, approximated with metaphors that capture the shape of the immensity without capturing its true depth. Around those stars orbit planets. We know this not from speculation but from measurement. The Kepler Space Telescope, launched in March of 2009, spent 4 years staring at a single patch of sky containing roughly 1,500,000 stars. It watched for transits, the almost imperceptible dimming of starlight caused by a planet crossing between its star and the telescope. The dimming is subtle almost beyond belief. An Earth-sized planet crossing a Sun-sized star blocks approximately 1/100% of the star's light. Detecting that signal required instruments of extraordinary sensitivity and years of patient observation. Kepler found thousands of planets, not dozens, thousands. And when scientists extrapolated those findings across the full stellar population of the galaxy, the conclusion was unambiguous. On average, every star hosts at least one planet. Many host several. The total planetary population of the Milky Way almost certainly exceeds 1 trillion individual worlds. 1 trillion planets. Some of those worlds orbit within the habitable zone of their stars, the narrow band of distance where temperatures permit liquid water to persist on a planetary surface. Not too close where oceans boil into steam, not too far where they freeze into kilometers of solid ice. The zone differs for each star depending on its luminosity, but around stars similar to our Sun, it falls at distances that produce surface conditions resembling Earth's. Conservative estimates suggest that between 2 and 4 billion rocky planets orbit within the habitable zones of Sun-like stars in the Milky Way alone. When red dwarf stars are included, and red dwarfs constitute roughly 70% of all stars in the galaxy, that number climbs toward 10 billion. 10 billion worlds where liquid water might flow. 10 billion chemical laboratories running experiments in molecular complexity across timescales measured in billions of years. And on at least one of them, the chemistry worked. On at least one of those 10 billion worlds, simple molecules assembled into more complex molecules, and complex molecules assembled into self-replicating structures. And self-replicating structures accumulated variations and competed and diversified, and eventually produced after roughly 4 billion years of iteration. a creature that built radio telescopes and particle accelerators and pointed cameras at the rings of Saturn and wept at the photographs. If it happened here, the logic of large numbers suggests it happened elsewhere, perhaps many elsewheres, perhaps billions of elsewheres. The same carbon chemistry operates identically in every corner of the galaxy. The same physical laws govern molecular assembly on a world orbiting a red dwarf 40 light-years away as on a world orbiting a yellow star in the Orion arm of the Milky Way. There is no reason, no physical, chemical, or biological reason why the processes that produce life on Earth should be unique to Earth. This is the foundation of what makes the silence so strange. If the galaxy contains billions of potentially habitable worlds, and if the chemistry of life is a natural consequence of those conditions rather than a miraculous accident, then the Milky Way should be populated. Not densely populated perhaps, but populated, scattered with islands of biology at various stages of complexity. Some still microbial, some perhaps multicellular, some conceivably technological, some possibly ancient beyond our ability to imagine. Civilizations that ignited while Earth was still a ball of cooling magma. Civilizations that have had billions of years to master physics, to build instruments to reach outward, and yet the sky is silent. No unambiguous signal has ever been received from another intelligence. No artifact of alien engineering has been identified anywhere in the solar system. No probe of non-terrestrial origin has been detected approaching our world. The search for extraterrestrial intelligence, which has been scanning the sky for electromagnetic signals since Frank Drake pointed a radio telescope at 2 nearby stars in 1960, has accumulated more than 6 decades of data from thousands of stellar targets and found nothing that cannot be explained by natural astrophysical processes. 60 years of listening into a galaxy that should by the numbers be full of voices. Silence. This is the Fermi paradox, named for the physicist Enrico Fermi, who posed the essential question over lunch at Los Alamos in 1950. If the conditions for intelligent life are common, and if a civilization even slightly older than ours has had time to spread across the galaxy, which by some calculations should take only a few million years, a trivial span against the galaxy's 13 billion year history, then where is the evidence? Where are the signals, the probes, the megastructures, the unmistakable fingerprints of minds other than ours? Where is everybody? Many answers have been proposed. Perhaps intelligent life is extraordinarily rare, a vanishingly improbable accident that happened once and only once in the observable universe. Perhaps civilizations routinely destroy themselves before achieving the capability for interstellar outreach. Perhaps advanced civilizations deliberately conceal their presence. Perhaps they have transcended physical existence in ways our current understanding cannot anticipate. Perhaps they are here and we lack the instruments to recognize them. Each of these answers carries its own problems. Each leaves residual questions that resist resolution, and each, when examined carefully, tends to underestimate a simpler and more devastating possibility. The universe may be full of life. Civilizations may exist in numbers far exceeding our most optimistic estimates, and it may not matter at all, because the universe was not built for meetings. The same physical laws that allow stars to burn and planets to form and carbon to assemble into living tissue have constructed a prison of distance, energy, time, and geometry, so total, so absolute, so deeply embedded in the structure of reality itself, that two civilizations may arise, flourish, reach the peak of their technological capability, and vanish without ever exchanging a single photon of intentional communication, without ever knowing the other existed, without leaving behind any evidence that could be found before the other civilization itself disappeared. Not because they failed to try, not because they lacked the intelligence, not because the galaxy was empty, but because the architecture of the cosmos ensures that existence and accessibility are two entirely different things. If you enjoy journeys that permanently alter how you see the universe you inhabit, consider taking a moment to like this video and subscribe to this channel. It genuinely helps this work reach the people who need it most. Now find yourself a quiet space. Set aside whatever else is pressing on your mind. What follows will take time. It will cover distances that will make your home galaxy feel like a small room. It will examine barriers so fundamental that no engineering, however advanced, can fully overcome them. Get comfortable. Let's begin. Start with the number that should fill you with hope and then watch it become something else entirely. 10 billion. That is a conservative estimate for the number of potentially habitable worlds in the Milky Way worlds, where liquid water might persist, where temperatures fall within a range that organic chemistry can tolerate, where the raw ingredients for biology are present in usable form. 10 billion individual chances. 10 billion separate arenas where the experiment of life could be running at this moment. Now, ask a different question. Not how many worlds, but how many civilizations. And not civilizations in the broad sense of any group of organisms living together, but civilizations in the specific and narrow sense that matters for this discussion. Civilizations capable of building instruments that can be detected across interstellar distances. Civilizations that have crossed the threshold from biology into technology, from organisms that react to their environment into organisms that deliberately reshape it, that build radio transmitters, that launch objects into orbit, that point telescopes at the sky and wonder. This narrower definition changes everything. On Earth, life appeared approximately 3.7 billion years ago, almost as soon as conditions permitted. But technological civilization, the specific configuration of intelligence and infrastructure that makes a species detectable across light years, has existed for approximately 2 centuries. 2 centuries out of 3.7 billion years of biological history. The ratio is roughly 1 part in 18 million. For every 18 million years that life has existed on this planet, technology has existed for 1 year. If that ratio is typical and there is no particular reason to believe Earth is anomalous in this respect, then the fraction of a planet's biological window during which it hosts a detectable technological civilization is extraordinarily small. The galaxy might contain 10 billion living worlds and still contain only a handful of technological ones at any given moment. Not because technology is impossible, but because it is brief. Because the window during which any particular planet hosts creatures capable of interstellar communication is measured against the sweep of cosmic time almost imperceptibly thin. Define that window generously. Assume a typical technological civilization persists for 1 million years. This is more than 5,000 times longer than human civilization has existed in any form, and roughly 3 times longer than the entire existence of the genus Homo. It is an assumption of extraordinary optimism about civilizational durability. And yet, even under this generous assumption, a civilization lasting 1 million years occupies only 1/13,000th of the galaxy's total history, a flash, a spark, brief beyond any human analog. Now scatter these sparks across the Milky Way and ask how many burn simultaneously. The Drake equation, formulated by astronomer Frank Drake during a conference at Green Bank, West Virginia in 1961, provides a framework for this estimate. It multiplies together a chain of factors: the rate of star formation, the fraction of stars with planets, the fraction of planets in habitable zones, the fraction of habitable worlds that develop life, the fraction of living worlds that produce intelligence, the fraction of intelligent species that develop detectable technology, and the average lifespan of such civilizations. Most of these factors remain poorly constrained by observation, but even conservative values for each term produce estimates that range from a handful to several thousand active civilizations in the galaxy at any given time. Take a middle position. Assume 1,000 technological civilizations burning simultaneously across the Milky Way's 400 billion stars and trillion planets. 1,000 is an optimistic figure by many serious estimates, but adopt it because it is generous, because it loads every assumption in favor of contact, because if contact fails under these conditions, the failure becomes all the more illuminating. 1,000 civilizations distributed through the Milky Way's disk. Now, measure the distances between them. The Milky Way is not a point. It is a flattened spiral disk, approximately 100,000 light-years in diameter and roughly 2,000 light-years thick at the position of our solar system. Its total volume, treating it as a cylinder, approaches 15 trillion cubic light-years. Scatter 1,000 civilizations randomly through that volume and calculate the average distance between nearest neighbors. The mathematics of three-dimensional spatial distributions yields a straightforward answer: approximately 1,000 light-years. 1,000 light-years between nearest neighbors under the assumption of 1,000 simultaneous civilizations, a figure that most serious researchers would consider extremely generous. Under more conservative assumptions of 10 or 100 civilizations, the average nearest neighbor distance climbs to roughly 6,000 or 3,000 light-years respectively. But even at 1,000 light-years, the number resists comprehension. Light itself, moving at approximately 300,000 kilometers per second, the absolute maximum speed permitted by the laws of physics, needs 1,000 years to cross that gap. A radio signal broadcast today from a civilization 1,000 light-years away was transmitted when the Byzantine Empire still existed, when the Song dynasty ruled China, when Europe had not yet experienced the Renaissance. If that civilization responded immediately upon receiving our first radio transmissions, which reached that distance only within the last century, the reply would not arrive for another 900 years. 1,000 years for the nearest possible neighbor, under the most optimistic assumptions. Under realistic assumptions, the number is 3 to 6 times larger. Under pessimistic but scientifically defensible assumptions, it is 10 to 15 times larger. The universe that the mathematics describes is not one in which civilizations are shouting across modest distances in a crowded neighborhood. It is one in which each civilization occupies its own vast, echoing silence, separated from the nearest other mind by a gulf that light itself takes millennia to cross. Hold that image. 1,000 years of void between you and the nearest other mind in the galaxy, measured in the fastest thing the universe permits. And that is the optimistic case. That is 1,000 civilizations, the most generous estimate and most serious researchers would entertain, producing the shortest, plausible, nearest neighbor distances. The universe is not small, and the civilizations within it, however numerous, are very far apart. But distance alone, however vast, is theoretically a problem of patience and engineering. Given enough time, given sufficient energy, perhaps even a gap of 1,000 light-years could be crossed by something. A vessel, a probe, a signal. The universe, however, does not grant unlimited time. It does not grant unlimited energy. It imposes constraints, on both constraints that arise not from the limits of any particular technology, but from the deepest and most immovable principles of physical law. The first of those constraints is not a wall you can see from a distance. It is a wall you discover only when you begin to run toward it, and the closer you approach it, the more violently it pushes back. It is the speed of light, and it is absolute. 1416, Claude responded. In the spring of 1905, a young man sat at a desk in the Swiss Federal Patent Office in Bern and dismantled the architecture of the universe. In the spring of 1905, a young man sat at a desk in the Swiss Federal Patent Office in Bern and dismantled the architecture of the universe. He was 26 years old. He had failed to secure an academic position after graduating from university. His application for a teaching post had been rejected. He worked 6 days a week, reviewing patent applications, a job that paid modestly and demanded enough attention to occupy the hands, but not enough to silence the mind. In his spare hours, in the margins of his official duties, he was thinking about light. Specifically, he was thinking about what it would look like to chase a beam of light. If you ran alongside a beam of light at the same speed it traveled, what would you see? Would the light appear to stand still beside you the way a car appears motionless when you drive alongside it at the same speed on a highway? Classical physics said yes. The equations of electromagnetism developed by James Clerk Maxwell in the 19th century said no. The two frameworks gave irreconcilable answers to the same question. Something was wrong, not with the measurements, not with the mathematics, with the assumptions buried so deeply inside the foundations of physics that no one had thought to question them. Albert Einstein questioned them. What he discovered, or rather, what he derived from first principles over the course of several weeks of concentrated thought, was that the conflict between classical mechanics and electromagnetism could be resolved only by abandoning two assumptions so fundamental that they felt less like assumptions and more like the texture of reality itself. The first was that time flows at the same rate everywhere, independent of motion. The second was that lengths are fixed, independent of the speed at which they are measured. Both assumptions Einstein showed are wrong. Wrong in principle always at every velocity, with consequences that become measurable only when speeds approach that of light. The paper he published in June of 1905 was titled with characteristic understatement on the electrodynamics of moving bodies. It introduced the special theory of relativity, and embedded within its mathematics quiet and absolute was a conclusion that would echo through every subsequent discussion of interstellar travel, interstellar communication, and the accessibility of other civilizations. Nothing that carries mass can reach the speed of light. Not approximately reach it. Not approach it asymptotically to within some small remainder. Cannot reach it. Period. The speed of light in vacuum, approximately 2,99792 kilometers per second, is not a velocity that massive objects travel slowly through and gradually approach. It is a boundary condition of space-time itself. It is the rate at which causality propagates through the universe, and it is a wall so absolute that more than a century of experimental physics, including every particle accelerator ever built, every atomic clock ever synchronized, every GPS satellite ever launched, has done nothing but confirm its authority. To understand why this wall is so unyielding, you need to understand what happens to an object as it accelerates toward it, not what happens in the intuitive Newtonian sense where faster simply means more kinetic energy, and the relationship between the two is clean and linear. What actually happens according to a universe that has been tested to extraordinary precision and found to behave exactly as relativity predicts. Three things happen, three interlocking effects, each arising from the same mathematical structure, each reinforcing the others, each individually sufficient to complicate interstellar travel enormously, and together forming a barrier of remarkable completeness. The first is relativistic mass increase. Under Newtonian mechanics, the force required to accelerate an object depends only on its rest mass and the desired acceleration. Double the force, double the acceleration. The relationship is linear and well-behaved. Under special relativity, this relationship breaks down as velocity increases. The effective resistance of an object to further acceleration, what physicists call its relativistic mass, grows according to a mathematical function called the Lorentz factor. Named after the Dutch physicist Hendrik Lorentz, who derived it before Einstein, provided the physical interpretation. This factor starts near 1 at low velocities and climbs toward infinity as velocity approaches the speed of light. At 10% of light speed, the Lorentz factor is approximately 1.005. The object resists acceleration as though it were 0.5% heavier than at rest. Negligible. At 50% of light speed, the factor reaches approximately 1.15, a 15% increase in effective mass. Noticeable but manageable in principle for a civilization with access to sufficient energy. At 90%, the factor climbs to 2.29. The object now resists acceleration, as though it had more than doubled its rest mass. At 99%, the factor reaches 7.09. At 99.9%, it is 22.4. At 99.99%, it approaches 71. The curve steepens without limit, approaching infinity as velocity approaches the speed of light. To actually reach light speed, you would need to supply an infinite amount of energy to any object with mass. Not a very large amount. Not an astronomically large amount. Infinite. This is not an engineering problem. It is not a funding problem. It is a mathematical boundary as absolute as the impossibility of dividing by zero. The wall does not get harder to breach as you approach it. It becomes infinitely hard simultaneously at the moment of arrival. The speed of light is not a record waiting to be broken. It is the edge of a cliff that does not have a bottom. The second effect is time dilation. A clock aboard a vessel, moving at a significant fraction of light speed, ticks more slowly than a clock at rest. This is not a mechanical effect, not the result of vibration or acceleration damaging the clock's mechanism. It is a fundamental feature of how time itself flows at different velocities. Time is not a universal river moving at the same rate everywhere. It is a local phenomenon shaped by the velocity of the observer, and its rate of passage differs between a moving vessel and a stationary point of reference in ways that become dramatic at relativistic speeds. At 50% of light speed, time aboard the vessel passes at roughly 87% the rate of time at rest. For every 10 years that pass on the ship, 11.5 years pass outside it. At 90% of light speed, the ratio drops to 44%. For every 10 years aboard, 23 years pass in the external universe. At 99% shipboard time, crawls at barely 14% of the external rate. For every 10 years the crew experiences, 71 years pass at the origin destination. This effect is sometimes presented as a gift, a way to cheat the distance problem by compressing the subjective experience of a long journey. And for the travelers themselves, it does compress the experience. A journey of 10,000 light-years at 99% of light speed would take just over 10,000 years in the external universe, but only roughly 1,400 years is experienced by the crew. The crew ages 14 centuries instead of 10 millennia. But the compression is an illusion of perspective. The sending civilization must wait the full 10,000 years. The destination civilization must still exist when the vessel arrives, not in 14 centuries, but in 10,000 years of external elapsed time. The universe does not grant a discount on the duration of the journey merely because the passengers experience a fraction of it. Time dilation changes who bears the weight of the weight. It does not reduce the weight. It is a perceptual shift. It is not a shortcut. The third effect is length contraction. From the perspective of a vessel moving at relativistic speeds, distances in the direction of travel appear compressed. At 90% of light speed, a star that sits 10 light-years away in the rest frame appears from the ship's frame of reference to be only 4.4 light-years distant. This contraction is real in the sense that it is measurable and consistent. It is not an optical illusion or an artifact of how light reaches the ship's instruments. It is a genuine feature of the geometry of space-time, as experienced by a moving observer, and yet it changes nothing about the cost of the journey. The energy required to make the trip corresponds to the full, uncontracted distance as measured in the rest frame. The origin and destination measure the full 10 light-years. The fuel consumed reflects the full 10 light-years. Length contraction alters what the travelers perceive. It does not alter what the journey demands. 3 effects. 3 ways in which the universe reshapes itself in response to velocity. None of them are theoretical speculations awaiting experimental confirmation. All of them are operational realities that human technology already accounts for in daily practice. The Large Hadron Collider at CERN accelerates protons to 99.9999991% of the speed of light. At that velocity, the Lorentz factor approaches 7500. The protons behave in terms of their resistance to further acceleration, as though each one were 7500 times more massive than a proton at rest. The energy required to push them through each additional increment of velocity matches Einstein's equations to a precision that exceeds 12 significant figures. Every collision inside the LHC is a confirmation of special relativity at energies and velocities that human intuition was never built to process. The global positioning system, the network of satellites that tells your phone where it is on the surface of the Earth, would drift by approximately 10 kilometers per day if its software did not correct for relativistic time. Differences. The satellites move fast enough and sit high enough in Earth's gravitational field that their clocks tick at slightly different rates than ground-based receivers. The engineers who built the system accounted for this. They had to. Without the relativistic correction, GPS would be useless within hours of activation. Special relativity is not a hypothesis. It is embedded in the technology that tells you where to turn. Now, carry these principles beyond the physics classroom and into the problem of interstellar travel. Watch what the Lorentz factor does to the energy budget of a realistic mission. Not an abstract point particle, but a vessel of meaningful size, something capable of carrying equipment, crew, life support provisions for a journey lasting centuries. Give it a payload mass of 1,000 metric tons. This is roughly the mass of a large naval destroyer. It is a conservative figure for a vessel attempting to cross interstellar distances, a skeleton crew mission with minimal redundancy. Larger and more capable vessels would mass 10 or 100 times more. But start with 1,000 tons and grant the physics every possible advantage. Accelerate this vessel to 1% of the speed of light, roughly 3,000 kilometers per second. This is nearly 200 times faster than the New Horizons probe, the fastest spacecraft humanity has ever launched, which reached approximately 16 kilometers per second during its Jupiter gravity assist. 1% of light speed is so far beyond anything in the human engineering record that it qualifies by any reasonable measure as extraordinary. The kinetic energy required is approximately 4.5 times 10 to the 18th joules. This is roughly equivalent to the combined energy released by 20 of the largest thermonuclear weapons ever detonated, including the Soviet Tsar bomber, which released approximately 50 megatons of explosive energy in October 1961 over Novaya Zemlya. 20 of those devices, every joule directed into a single payload. And 1% of light speed is essentially useless for the distances involved. At 1% of light speed, the journey to a civilization 1,000 light-years away, the optimistic nearest neighbor distance, takes 100,000 years, longer than the entire existence of anatomically modern humans. The vessel would arrive to find its home civilization transformed beyond recognition or extinct. It would arrive to find the destination civilization similarly aged by 100 millennia of history transformed or gone. 1% of light speed does not solve the distance problem, it merely highlights it. Increase the velocity to 10% of light speed. The journey compresses to 10,000 years, shorter by an order of magnitude, still vastly longer than any human civilization has endured in recognizable form. And the kinetic energy of the payload has not increased by a factor of 10, as Newtonian intuition would suggest. It has increased by roughly a factor of 100 to approximately 4.5 times 10 to the 20th joules. This approaches the total energy consumption of human civilization across an entire year. Every power plant, every reactor, every solar farm, every combustion engine on Earth running continuously for 12 months produces energy roughly equal to the kinetic energy alone of this single vessel moving at 10% of light speed. And kinetic energy is only part of the story. Any vessel must decelerate upon arrival. Decelerating from 10% of light speed requires the same energy expenditure as accelerating to it. The round trip doubles the requirement again. A vessel that accelerates cruises, decelerates, re-accelerates for the return journey, and decelerates again at home requires roughly 4 times the one-way acceleration energy. 4 years of total human energy output for a single modest vessel on a single round trip. But even this accounting ignores the most devastating constraint of all the rocket equation. Any vessel that carries its own propellant must accelerate not just the payload, but the propellant itself. And the propellant needed to accelerate the propellant, and the propellant needed to accelerate that propellant. The compounding is relentless and exponential. For chemical rockets, the fuel-to-payload ratio required to reach even 1% of light speed exceeds numbers that have no physical meaning the fuel mass would need to exceed the mass of the observable universe. Chemical rockets are not inadequate for interstellar travel because we lack sufficiently advanced chemistry. They are inadequate because the energy density of chemical bonds falls short of the requirement by more than 40 orders of magnitude. Nuclear fusion improves the situation considerably. Fusion of deuterium and helium 3 converts approximately 0.4% of the fuel mass into energy, a dramatic improvement over chemical combustion. A fusion-powered spacecraft could theoretically reach velocities of several percent of light speed, with fuel-to-payload ratios in the range of tens to hundreds. Project Daedalus, a detailed engineering study conducted by the British Interplanetary Society during the 1970s, proposed a 2-stage fusion rocket capable of reaching Barnard's star approximately 6 light-years away at roughly 12% of light speed. The fully fueled vehicle massed approximately 54000 metric tons to deliver a payload of roughly 450 tons, a fuel-to-payload ratio exceeding 100 to 1, and this was for an uncrewed flyby mission to a destination 6 light-years distant, at a speed that would still require over 8,000 years to reach a civilization 1,000 light-years away. Scale the velocity upward, and the fuel ratio does not climb linearly, it climbs exponentially. At 30% of light speed, the required fuel mass for a fusion rocket begins to approach the mass of small moons. At 50%, it exceeds the mass of large asteroids by orders of magnitude. The rocket equation does not merely make interstellar travel expensive. At relativistic velocities, it makes it fuel logistically incoherent. No vessel can carry the fuel it needs to reach the speeds that would make the journey meaningful. Matter-antimatter annihilation offers the highest conceivable energy density. When a particle of matter meets its antiparticle, both are converted completely into energy, according to Einstein's most famous equation, 100% mass-to-energy conversion, approximately 250 times more efficient than the best fusion reactions. In principle, a matter-antimatter drive could approach the speed of light with fuel-to-payload ratios that remain physically manageable. In practice, the obstacle is manufacturing. The total antimatter produced by every particle accelerator on Earth since the technology was invented amounts to approximately 20 nanograms, 20 billionths of a gram. To produce even 1 gram of antimatter at current accelerator efficiencies would require energy inputs rivaling the annual electrical output of an entire nation. To produce the kilograms or tons of antimatter needed to propel an interstellar vessel would require energy inputs that dwarf anything human civilization currently produces. The most efficient conceivable fuel requires more energy to manufacture than the fuel itself will provide during the mission. The efficiency advantage is theoretically real, it is practically inaccessible. Consider what this accumulation of constraints means when assembled into a single picture. To cross the distance to the nearest plausible civilizational neighbor, even under the most optimistic assumptions about how many civilizations exist, at a speed that makes the journey achievable within any reasonable time frame, requires either fuel masses exceeding the mass of planets or energy, inputs exceeding the annual output of stars, or both. The speed limit prevents fast travel. The energy scaling makes fast travel ruinously expensive. The rocket equation ensures that the fuel needed for fast travel outweighs any conceivable vessel. And these are not 3 separate problems that might be solved independently. They are 3 manifestations of the same underlying physics, arising from the same equations, pointing toward the same conclusion. The universe permits slow travel across interstellar distances. It permits a vessel to crawl at 1% of light speed across 100,000 years of void. It does not forbid this. What it forbids through the interlocking constraints of the speed limit, the Lorentz factor, and the rocket equation is doing so in any time frame that preserves the purpose of the journey. You can cross the distance. You cannot cross it while anyone who matters is still waiting. This is the energy abyss, not a valley that deeper pockets might fill. An abyss, a gap between what physics permits in principle and what physics makes accessible in practice, so deep that no civilization operating within the laws of nature has an obvious path across it. But even this devastating barrier addresses only the question of whether a vessel can physically make the crossing. It says nothing about whether anyone will be there to meet it when it arrives. And the universe, it turns out, has a third constraint waiting in the shadows. One that operates not in the dimensions of space or energy, but in the dimension that runs silently beneath all the others: time. And time, of all the barriers, may be the one that closes the door most quietly and most permanently. There is a staircase buried inside the mathematics of special relativity. It begins at a step you can almost imagine climbing, and then it keeps going. Each step upward does not add to the difficulty of the one before it. It multiplies it. The staircase does not have a top. It has a ceiling, and the ceiling is infinite, and every step you take toward it demands more than all the steps beneath it combined. To understand what interstellar travel actually costs, you have to climb this staircase slowly. You have to pause on each step and look down at how far you have come, and then look up at how far you still have to go, and feel the weight of what the numbers are telling you. Because the numbers are not abstractions. They are the universe's answer to the question of whether civilizations can reach each other, and the answer they give is not impossible. It is something more precise and more devastating than impossible. It is at what cost? Begin at the bottom step, 1% of the speed of light, approximately 3,000 kilometers per second. This velocity is so far beyond anything humanity has achieved that it deserves a moment of reflection before the mathematics begins. The New Horizons spacecraft launched in January of 2006, and currently the fastest human-made object ever sent into deep space travels at approximately 14 kilometers per second. 1% of light speed is roughly 214 times faster. If New Horizons were traveling at 1% of light speed, it would have crossed the distance to Pluto, a journey that took the actual spacecraft 9.5 years in approximately 17 hours. 1% of light speed feels, by any human measure, extraordinary. By the measure of interstellar distances, it is essentially standing still. The kinetic energy required to accelerate a payload of 1,000 metric tons to 1% of light speed is approximately 4.5 times 10 to the 18th joules. To give this number texture, the largest nuclear weapon ever detonated, the Soviet Tsar bomber, released approximately 2.1 times 10 to the 17th joules of energy. The kinetic energy of our vessel at 1% of light speed is roughly 21 times greater than the energy of the largest thermonuclear explosion in human history, concentrated entirely into the motion of a single object. It is an amount of energy so far beyond current engineering capability that describing it as ambitious understates the case considerably. And yet 1% of light speed solves nothing. At this velocity, the journey to a civilization 1,000 light-years away takes 100,000 years. 100,000 years is longer than the entirety of recorded human history multiplied by 40. It is longer than the time since Homo sapiens first left Africa. By the time the vessel arrived, the civilization that built it would have undergone changes so profound as to make the original mission unrecognizable. The destination civilization would itself have aged by 100 millennia. Both the sender and the receiver would be geological footnotes by the time contact was made. 1% of light speed is a dead end. The energy cost is enormous and the result is nothing. Step up, 10% of light speed, approximately 3,000 kilometers per second. Now, the journey to a civilization 1,000 light-years away compresses to 10,000 years, still longer than all of recorded human history, but shorter by an order of magnitude. Progress, in a sense. The question is what that order of magnitude of improvement costs. The kinetic energy of 1,000 metric tons at 10% of light speed is approximately 4.5 times 10 to the 20th joules. The increase from 1% to 10%, a tenfold increase in velocity, has produced not a tenfold increase in energy, but a 100-fold increase. This is the first clear sign of what the staircase does. Velocity increases linearly. Energy increases with the square of velocity, and then as relativistic effects begin to bite faster than the square. At 10% of light speed, relativistic corrections add roughly 0.5% to the effective mass. The classical approximation is still reasonably accurate, but the curve has begun to bend. 4.5 times 10 to the 20th joules. The total energy consumption of human civilization, every power plant, every reactor, every oil well, every solar panel, every combustion engine, on every road in every country on Earth, amounts to approximately 5.8 times 10 to the 20th joules per year. The kinetic energy of our vessel at 10% of light speed approaches the total annual energy output of an entire planetary civilization. Every joule produced by every energy source on Earth for 12 consecutive months redirected into a single object. This is the kinetic energy of the payload alone. It does not account for the fuel. Any vessel that carries its own propellant must accelerate the propellant alongside the payload. The Tsiolkovsky rocket equation, derived by the Russian mathematician Konstantin Tsiolkovsky in 1903, describes the mathematical relationship between the mass of a rocket, the mass of its propellant, and the velocity it can achieve. The equation is elegant and merciless. It states that the ratio of initial mass to final mass, the ratio of fully fueled vessel to empty vessel after all fuel is burned, grows exponentially with the desired velocity divided by the exhaust velocity of the propulsion system. For a fusion rocket, the most credible near-future candidate for interstellar propulsion, the exhaust velocity approaches a few percent of light speed. To accelerate a payload to 10% of light speed and then decelerate upon arrival, the fuel-to-payload ratio climbs into the range of hundreds to 1. A vessel delivering 1,000 tons of useful payload to its destination would need to begin its journey massing hundreds of thousands of tons, almost entirely fuel. The fuel dwarfs the vessel. The vessel is a small capsule balanced atop a mountain of propellant, and this fuel must itself be accelerated from the moment of launch, which means additional fuel is needed to accelerate the fuel, which means additional fuel is needed for that. The compounding does not stop. The rocket equation spirals exponentially, demanding that each increment of additional velocity requires a disproportionately larger investment in propellant mass. At 10% of light speed with fusion propulsion, the total mass ratio, including the fuel needed to accelerate the fuel, places the total mission mass in the range of several million tons for a 1,000-ton payload. Several million tons for one vessel, traveling one way to a destination that is, under optimistic assumptions, the closest possible civilizational neighbor. Step up again, 30% of light speed. The journey to a civilization 1,000 light-years distant now takes approximately 33,000 years. Still longer than all of recorded human history, but shorter than the span of many ancient civilizations measured against the deep past. Relativistic effects have become significant. The Lorentz factor, at 30% of light speed, is approximately 1.048, meaning the effective mass has increased by nearly 5% above rest mass. The kinetic energy of the payload climbs to roughly 4.3 times 10 to the 21st joules, nearly 10 times the total annual energy consumption of human civilization. Nearly a decade of every joule produced by every energy source on Earth concentrated into a single vessel. But the fuel problem has grown catastrophic. At 30% of light speed, the mass ratio demanded by the rocket equation for a fusion drive, including deceleration, at the destination, exceeds 10,000 to 1. The 1,000-ton payload sits at the tip of a propellant mass exceeding 10 million tons. This is heavier than a small asteroid. Assembling, fueling, and launching such a vehicle would require industrial infrastructure operating at a scale that dwarfs anything in human history. Step up again, 50% of light speed. The Lorentz factor has climbed to approximately 1.155. Relativistic mass increase has added more than 15% to the effective payload. The kinetic energy of the 1,000-ton payload reaches approximately 1.4 times 10 to the 22nd joules, more than 20 times the total annual energy consumption of human civilization. 24 years of total global energy output condensed into the motion of a single object. The journey to a civilization 1,000 light-years away now takes approximately 2,000 years, 2 millennia. The Roman Empire at its height endured for roughly 5 centuries before fragmenting. 2,000 years is 4 times that span. It encompasses the entire recorded history of Christianity, Islam, and the Enlightenment, with centuries to spare. At 50% of light speed, the fuel mass demanded by the rocket equation becomes difficult to describe without losing the thread of meaning. For a fusion drive attempting to reach 50% of light speed and then decelerate, the mass ratio exceeds 100 million to 1. The required fuel mass is not measured in asteroid equivalents, it is measured in small planet equivalents. The total mass of propellant needed to deliver 1,000 tons to 50% of light speed and slow it to a stop exceeds the mass of a body the size of a dwarf planet. The engineering required to process, contain, and expel this quantity of fusion fuel surpasses anything conceivable within any near-future extrapolation of human technology. And the energy budget for the complete mission, including the energy needed to produce and handle the fuel, climbs into a regime measured not in years of human energy consumption, but in fractions of solar output. The Sun radiates approximately 3.8 times 10 to the 26th joules per year. The total mission energy for a 50% light speed crossing, accounting for fuel production and expenditure, approaches minutes of total solar output. Not the energy Earth receives from the Sun. The total energy the Sun emits in all directions simultaneously. Minutes of that. Step up again. 90% of light speed. The Lorentz factor has reached 2.29. The effective mass of the payload is more than twice its rest mass. The kinetic energy climbs to approximately 1.6 times 10 to the 23rd joules. More than 200 years of total human energy consumption. 2 centuries of every joule produced by every source on Earth delivered into the kinetic energy of a vessel that, from its own frame of reference, has traveled to its destination in only about half the time an external observer measures. At 90% of light speed, a journey to a civilization 1,000 light-years away takes approximately 1100 years, as measured by an external clock, but only roughly 480 years, as experienced by the crew due to time. Dilation. Less than 5 centuries of subjective travel. For the crew, this is meaningful. They would age less than 500 years before arriving. If they entered a form of metabolic suspension, the subjective duration could be made arbitrarily shorter still. But the external universe does not compress. The destination civilization must persist for 1100 years after the vessel is launched. Not 480 years. 1100. The sending civilization must maintain its purpose and institutional memory across that same span, and the fuel requirements have become detached from any physical grounding. At 90% of light speed, the rocket equation demands a mass ratio so extreme that the required propellant exceeds the mass of large planets. The total mission energy for a one-way trip with deceleration climbs toward the equivalent of decades of total solar output. Not seconds, not minutes. Decades of every joule the Sun radiates in all directions, funneled into the acceleration and deceleration of a vessel carrying the mass of a naval destroyer. A Kardashev Type II civilization, one that has achieved the capacity to harness the complete energy output of its host star, would need to save that output for decades before it could afford a single one-way crossing at 90% of light speed. A round trip would require over a century of stellar savings. And this is under the assumption that the civilization's star is similar in luminosity to our Sun. Civilizations orbiting dimmer red dwarfs would face energy deficits even more severe. There is a number that deserves particular attention here. At 99% of light speed, the Lorentz factor reaches 7.09. The effective mass of the payload is 7 times its rest mass. The kinetic energy of the 1,000-ton payload approaches 5.4 times 10 to the 23rd joules, roughly 1,000 years of total human energy consumption. The fuel mass required by the rocket equation for a fusion drive attempting 99% of light speed with deceleration exceeds any physical object in the solar system other than the Sun itself. And at 99.9%, the Lorentz factor climbs to 22.4. The wall is visible now, close and absolute, steeper than anything that precedes it. Each additional decimal place of velocity toward the speed of light demands more than all the energy that came before. The curve does not merely steepen, it accelerates toward infinity. The universe is not being arbitrary. It is not imposing this escalation through some cosmic sense of cruelty. The energy scaling follows directly from the mathematics of space-time, from the same geometric structure that produces every confirmed prediction of special relativity. It is the same framework that makes GPS satellites work, that predicts the precise decay rates of muons in cosmic ray showers, that describes the behavior of every particle that has ever been accelerated inside a collider. The staircase is not a theoretical artifact. It is a measured, confirmed, repeated feature of physical reality. Some proposals attempt to sidestep the rocket equation by abandoning the idea of a vessel that carries its own propellant. The most developed of these is the light sail concept, a spacecraft propelled not by onboard fuel but by the pressure of laser light striking a reflective surface. The Breakthrough Starshot initiative, announced in 2016, and backed by a consortium of scientists and entrepreneurs, proposes exactly this architecture. A ground-based laser array with a combined power of roughly 100 gigawatts, more than 3 times the total electrical generating capacity of the United Kingdom, focused onto a sail-bearing probe, massing approximately 1 gram. The probe would accelerate to approximately 20% of light speed within minutes, reaching the Alpha Centauri system in about 20 years. This is a genuine and serious engineering concept for robotic exploration of the nearest stellar system, but it does not address physical contact between civilizations separated by thousands of light years. A 1-gram probe cannot carry passengers. It cannot carry life support systems. It cannot carry the scientific and diplomatic equipment of a civilization attempting first contact. And it cannot decelerate at the destination. No laser array exists there to slow it down. The probe would scream through the target system at 60,000 kilometers per second, collecting data during a passage lasting hours, and continue into the interstellar void beyond. It is a flyby instrument, not a vehicle for meeting. Scaling the laser sail to larger payloads introduces its own geometric catastrophe. Radiation pressure scales with sail area, payload mass scales with volume. To carry a payload of 1,000 tons rather than 1 gram requires increasing the laser power, not by a factor of 1,000, but by a factor of roughly 1 trillion. A 100 gigawatt array becomes a 100 zettawatt array, a power output exceeding the total energy Earth receives from the Sun by 4 orders of magnitude. No physical array could generate or sustain such power. The concept, elegant and credible at gram scale, collapses under its own geometry when scaled to civilizational relevance. The Alcubierre warp drive, proposed by Mexican physicist Miguel Alcubierre in 1994, offers a more radical escape from the energy staircase. General relativity. Einstein's theory of gravity permits mathematical solutions in which a bubble of flat spacetime moves through the universe at arbitrary velocity by contracting space in front of it and expanding space behind it. A vessel inside the bubble would experience no acceleration and no relativistic mass increase. It would arrive at its destination in a fraction of the time light would require. The mathematics permit it, the physics almost certainly does not. The Alcubierre metric requires exotic matter, a substance with negative energy density that has never been observed in nature and may be forbidden by the same quantum field theory that underlies particle physics. Even setting aside this fundamental obstacle, calculations of the energy required to sustain the warp bubble converge on figures involving the conversion of Jupiter mass quantities of matter into exotic energy configurations. Some formulations suggest the energy requirement exceeds the total mass energy of a star. These are not engineering challenges awaiting clever solutions. They are mathematical demonstrations of how far outside the accessible parameter space the concept sits. The warp drive is a solution permitted by the equations and almost certainly denied by the universe. Strip away the speculation and the picture that remains is stark and unambiguous. The energy required to cross interstellar distances at speeds meaningful for making contact scales exponentially with velocity. The rocket equation compounds this requirement into fuel masses that exceed planets at relativistic speeds. Alternative propulsion concepts either require exotic matter that may not exist, or are physically limited to grain-scale payloads, or require energy sources equivalent to stars. The speed limit imposed by special relativity ensures that no amount of energy can push a massive object to light speed, and the curve of escalating cost ensures that approaching light speed demands energy approaching infinity. The universe is not malicious in constructing this barrier. It is consistent. The same constants that set the speed of light also determine the energy density of nuclear reactions, the mass energy equivalence of matter, and the geometry of space-time. These constants conspire without intent and without exception to make fast interstellar travel the most energetically expensive activity imaginable. Every joule of energy that exists in the observable universe could be directed toward a single vessel, and the vessel would still not reach the speed of light. Slow travel is permitted. Crawling across the void at 1 or 2% of light speed, burning through centuries or millennia, is physically allowed. What is not permitted is doing so on any timescale that preserves the meaning of the journey. The energy abyss and the speed limit together close one jaw of the trap. The other jaw waits in a dimension that physics discusses less dramatically, but that operates with equal finality. Not in space where the distances are measured in light years. Not in energy where the costs are measured in fractions of stellar output. In time, in the quiet, relentless forward motion of time which gives each civilization its window of existence and then closes that window without negotiation, without extension, and without regard for whether the journey across the void has been completed. There is a thought experiment that clarifies the temporal problem more precisely than any equation. Imagine a building, not a small building, a tower of 10,000 floors, each floor divided into hundreds of individual rooms, the total number of rooms approaching 1 million. The building has existed for a very long time. Residents have come and gone across its entire history. At any given moment, some rooms are occupied, others are empty. The building is never fully vacant, but it is also never fully occupied. Life moves through it in pulses, in waves, in isolated instances of presence, separated by long intervals of absence. Now add a constraint. Each resident occupies their room for exactly 15 minutes out of every year. They arrive at a random time, stay for their quarter hour, and then leave. The building operates on no schedule. There is no directory. No one knows when anyone else will be home. Your 15 minutes might fall at 3 in the morning on a Tuesday in February. Your nearest neighbor's 15 minutes might fall on a Saturday afternoon in October. The person 2 floors above you might have been home yesterday or might not arrive for another 8 months. You could live in that building for decades and never share a moment of simultaneous presence with another soul. Not because the building is empty, not because no one else lives there, but because the windows of occupancy are brief, randomly distributed, and completely uncoordinated. The building is full of people across its history. At any given instant, almost all of them are absent. This is the temporal condition of civilizations in the Milky Way. The galaxy has existed for approximately 13.8 billion years. It will continue to exist in some recognizable form for trillions of years beyond the present moment. Against this backdrop, a technological civilization that persists for 1 million years occupies a window so narrow that expressing it as a fraction produces a number the human mind cannot intuitively hold. 1 million years divided by 13.8 billion years is approximately 1 part in 13,000. If the entire history of the galaxy were compressed into a single calendar year, 1 million years would correspond to roughly 40 minutes. Not 40 days, not 40 hours, 40 minutes somewhere within a year whose duration you cannot see from end to end. The window opens, the window closes, and the galaxy continues turning indifferent to what burned briefly inside it. Begin with the most fundamental question of temporal overlap. 2 civilizations arise independently in the Milky Way. Each persists for 1 million years. What is the probability that their windows of existence overlap at all? That there is at least one moment in time when both civilizations are simultaneously alive and technological? The calculation is straightforward. Place 2 intervals of 1 million years each at random positions on a timeline of 13.8 billion years. The probability that they overlap depends on their combined length relative to the total timeline. Combined, the 2 windows span 2 million years. The total timeline spans 13.8 billion years. The probability of overlap is approximately 2 million divided by 13.8 billion, or roughly 1 in 7,000. For every 7,000 pairs of civilizations arising independently in the galaxy's history, approximately 1 pair will share any temporal overlap at all. 6,999 pairs will be separated in time, one civilization burning and fading long before the other ignites, the gap between them measured in millions of years of silence. This is the baseline probability before any consideration of spatial proximity, travel time, or the physical constraints discussed earlier. This is merely the probability that 2 civilizations exist at the same time, and it is already 1 in 7,000. But simultaneous existence is only the beginning of what contact requires. The civilizations must not merely coexist, they must coexist long enough for a physical journey between them to be completed. Recall the distances. Under optimistic assumptions of 1,000 simultaneous civilizations in the Milky Way, the nearest neighbor separation averages approximately 1,000 light-years. At 10% of light speed, requiring roughly a year of total planetary energy output for the acceleration alone, the one-way journey takes 10,000 years. For the mission to succeed, the destination civilization must remain technological and detectable for 10,000 years after the vessel is launched. 10,000 years. This is the minimum survival requirement placed on the destination civilization by the physics of the journey under the most optimistic assumptions about civilizational density and travel speed. 10,000 years is 5 times longer than all of recorded human history. It encompasses the entire span from the earliest Sumerian city-states to the present day multiplied by 5, and asks that the destination civilization survive all of it without collapse, transformation, or withdrawal from detectability. If the destination civilization's total technological lifespan is 1 million years, and the vessel must arrive within that window, then the vessel must be launched within the final 9,900,000 years of that window, equivalently within any 10,000-year segment of it. The probability that a randomly timed launch falls within the required arrival window is 10,000 divided by 1 million, 1 in 100, 1%. Compound this with the probability of temporal overlap, calculated earlier, 1 in 7,000, and the probability that two civilizations both exist simultaneously and that a journey between them can be completed during the destination. Civilization's technological window drops to approximately 1 in 700,000, and this calculation has not yet accounted for the spatial constraint. Not every pair of simultaneously existing civilizations will be close enough for travel to be feasible. The 1,000 light-year nearest neighbor distance is an average under optimistic assumptions. Many pairs will be separated by several thousand light-years, requiring journey times of tens of thousands of years, and pushing the survival requirement on the destination civilization toward the limits of any plausible civilizational lifespan. There is a further complication that the simple probability calculation obscures: the signal problem. A civilization cannot launch a vessel toward a destination it does not know exists. It must first detect the destination. Civilization receives some signal, observe some artifact, identify some spectral signature of technology in a distant planet's atmosphere. This detection depends on the destination civilization actively broadcasting or at minimum passively leaking electromagnetic signals in directions that happen to include the sender's location. But the signals travel at the speed of light. A signal received today from a civilization 1,000 light-years away was emitted 1,000 years ago. It describes the state of that civilization 1 millennium in the past. By the time the signal is received, analyzed, and a vessel is constructed and launched, a process that might itself require decades to centuries, the information on which the mission is based is between 1,000 and 1,200 years old. The destination has aged by that entire interval since the signal was sent. It may have transformed, it may have ceased broadcasting, it may no longer exist. The vessel is launched toward a past. It travels through a present. It arrives in a future. At no point in this sequence does the sending civilization have access to current information about the destination. The gap between the state of the destination when the signal was sent and the state of the destination when the vessel arrives spans the full light travel time plus the journey time, potentially 2,000 years or more, for a 1,000 light-year separation at 10% of light speed. During those 2,000 years, the destination civilization has continued its history, without interruption, without knowledge that a vessel is en route, and without any obligation to remain stable, detectable, or interested in contact. Now let the imagination move through one of these scenarios in detail, not as a thought experiment, but as a consequence of the mathematics, something that, if civilizations exist in the numbers the Drake equation allows, has almost certainly happened somewhere in the galaxy's long history. A civilization arises on a rocky world orbiting a sun-like star approximately 8,000 light-years from Earth. They develop technology roughly 3 million years ago, long before anatomically modern humans existed. They build radio telescopes, they scan the sky, After several centuries of systematic observation, they detect an anomalous signal from a star system roughly 4,000 light-years distant. The signal is faint, repeating, and structured in ways that cannot be explained by known natural processes. It is unmistakably artificial. It is unmistakably intelligence. The civilization responds, not with a radio reply that would take 4,000 years to arrive and another 4,000 to return. They respond by building a vessel. The project consumes 2 centuries of effort and resources, equivalent to the output of a significant fraction of their planetary economy. The vessel is designed to travel at 8% of light speed, the maximum their energy infrastructure can sustain for the acceleration phase. It carries a crew of several hundred, a vast library of their civilization's knowledge and equipment for establishing extended contact with whatever they find at the destination. The vessel launches. The journey takes 50,000 years. During those 50,000 years, the launching civilization continues its history. Cultures rise and fall within it. Languages evolve. The original purpose of the mission becomes for periods a matter of historical interest rather than active concern. But the civilization endures. It transforms as all things transform across sufficient time, but the institutional memory of the mission persists. The vessel continues. 50,000 years of void of cosmic ray bombardment, of the slow erosion of systems pushed far beyond their designed operational lifetimes. The vessel arrives. It enters the target star system and achieves orbit around the third planet, the world from which the signal was detected. From orbit, the crew surveys the surface. The planet is alive, unmistakably gloriously alive. The oceans are a deep and complex blue, threaded with the pigments of photosynthetic organisms. The continents are green and brown and textured with the features of active geology. Weather systems spiral across the atmosphere. The air contains oxygen at concentrations consistent with a biosphere of significant complexity and duration. But the surface shows no artificial structures, no geometric patterns visible from orbit, no city lights on the night side, no electromagnetic transmissions of any kind detectable across any frequency. The crew deploys atmospheric sampling probes. The air is breathable nitrogen-oxygen with trace gases consistent with a productive biosphere. They descend. They land on a continent that the ancient signal had suggested was the center of technological activity. They find forests. Dense, diverse, architecturally complex forests of organisms that fill every ecological niche with characteristic evolutionary creativity. They find rivers running clear over unmodified riverbeds. They find coastlines undisturbed by any structure or engineering. They search for ruins. After several years of surface exploration, they find them not spectacular ruins, not the stone monuments of a civilization that built for permanence, because this civilization had progressed beyond stone long before its end. What they find are subtle chemical anomalies in the soil. Concentrations of refined metals too pure to be geological, isotopic signatures in certain rock layers consistent with the products of nuclear reactions. The faint geometric outlines of what were once foundations now dissolved over tens of thousands of years of biological activity into faint discolorations in the earth, detectable only with instruments. The civilization they crossed 50,000 years of void to meet ended approximately 47,000 years ago. They missed them by 47 millennia, a gap that is measured against the journey they just completed almost nothing, 3,000 years short. If the destination civilization had lasted 3,000 years longer, a trivial extension relative to its total duration, the crew would have arrived to find cities, signals, minds capable of receiving them. Instead, they find a planet in the slow process of forgetting that intelligence ever walked it. The crew is not the first example of this scenario. They will not be the last. Across the galaxy's long history, in the rare instances where the energetic and temporal conditions align well enough for an interstellar mission to be attempted, this outcome, arrival at a functioning biosphere that has outlasted its civilization, may be among the most common results. The planet lives on, the intelligence does not. Or consider the inverse. A vessel launches toward a destination and arrives not too late, but too early. The signal that prompted the mission came from a world showing complex atmospheric chemistry, oxygen, methane signatures of active biology. The senders inferred correctly that a biosphere of significant complexity existed there. They inferred hopefully that such a biosphere might eventually produce intelligence. They launched a slow vessel at 3% of light speed, intending it as a generational ship, a vessel whose original crew would age and die during the journey, replaced by their children and grandchildren across the centuries, sustained by a closed ecological system and the institutional purpose passed down through generations. The journey takes 13,000,000 years. The vessel arrives. The target world is alive, beautifully abundantly alive, but its most complex organisms are roughly analogous to Earth's Cambrian fauna, multicellular, diverse, increasingly sophisticated, but nowhere near producing the neural complexity that leads to language technology or the capacity to recognize visitors. The biosphere is 13,000,000 years closer to intelligence than it was when the signal was first detected. It may reach intelligence in another 100 million years, or it may not. Evolution has no timetable and no obligation to produce minds. The travelers have arrived 100 million years early. There is no one to meet. There will not be anyone to meet within a time frame that any civilization could span. The vessel carries enough resources for perhaps 2 or 3 generations of life at its destination. The crew or their grandchildren will live out their lives on a living world that will not produce a consciousness capable of understanding their presence for longer than the gap between the age of dinosaurs and the present day. These scenarios are not tragedies in the emotional sense. They are outcomes. They are the natural consequences of a universe in which civilizations are brief, distances are vast, and the speed of information is limited to the speed of light. They are what happens when the mathematics of temporal mismatch plays out across the actual history of a galaxy that has been producing and extinguishing civilizations for billions of years. The stars themselves impose a version of this problem that operates on even longer timescales. A civilization that arose 3 billion years ago around a star that has since evolved off the main sequence, a star that has expanded into a red giant, engulfed its inner planets, and shed its outer layers to become a white dwarf, left no destination for a contemporary civilization to visit. The address still exists in the sense that a stellar remnant still occupies the position, but the habitable world is gone. The oceans that once supported chemistry are gone. Whatever life arose there, and whatever intelligence that life produced have been gone for so long that no chemical trace of their existence survives anywhere detectable from interstellar distances. The galaxy is not merely a spatial puzzle, it is a temporal one. The same volume of space that houses a young civilization today housed a different civilization millions of years ago and will house yet another civilization millions of years hence. The same cubic light years rotate through occupancy, like the rooms in that vast, uncoordinated building, sometimes occupied, mostly vacant, never or almost never occupied simultaneously by 2 civilizations close enough and aware enough of each other to make contact. There is one more dimension of the temporal problem that deserves explicit attention because it is rarely discussed, and yet it may be among the most decisive factors in the isolation of civilizations. Stars move. The Milky Way is not a static backdrop against which civilizations are positioned at fixed addresses. It is a rotating disk in which every star orbits the galactic center at a velocity determined by its distance from the core. The Sun orbits at approximately 220 kilometers per second, completing one full revolution of the galaxy every 230 million years. Over the course of a 50,000-year journey, the crossing time to a civilization 1,000 light-years away at 10% of light speed, the destination star moves approximately 11 light-years due to its own orbital motion. 11 light-years. This is nearly 3 times the distance to the nearest stellar system to Earth. A vessel launched toward the current position of a star, without accounting for this drift, would arrive to find empty space. The target has relocated to an address 11 light-years from where it was when the mission launched. 11 light-years is not a rounding error. At the vessel's own velocity of 10% of light speed, 11 light-years represents an additional 110 years of travel. Over longer journeys, the problem compounds. Across 5,000,000 years of travel time, the destination star moves approximately 110 light-years. Across 5 million years, it relocates by over 1,000 light-years, effectively placing it in a different region of the galaxy than the one from which the original signal was received. Accounting for this drift requires predicting the gravitational influences on the destination star's orbit across the full journey duration. Stars bob vertically through the galactic disk in cycles of 60 to 70 million years. They experience perturbations from spiral arms, encounters with molecular clouds, and the cumulative gravitational nudges of every massive object they pass within thousands of light-years. Over timescales of millions of years, stellar trajectories become chaotic in the technical sense, sensitive to initial conditions in ways that make precise prediction essentially impossible. The destination is not a fixed point, it is a moving target, following a path that grows increasingly uncertain with every additional century of projection. Compile all of this. The brevity of civilizational windows measured against the galaxy's 13 billion year history. The 1 in 7,000 probability of temporal overlap for any two independently arising civilizations. The survival requirement imposed on the destination civilization by the journey time. The signal problem, the fact that all information about the destination is old by exactly the light travel time when received, and older still by the time a vessel arrives. The stellar motion problem, the target relocating across the full duration of the crossing. Each of these factors operates independently. Each carries its own probability of failure. Stack them, and the compound probability of successful contact drops with each additional requirement, as surely as a series of independent coin flips will eventually produce a sequence of tails that stretches to the horizon. The universe creates civilizations. It gives each one a window. The window is brief. The distances are vast. The speed of information is finite. The stars drift, and the windows close without warning, without ceremony, and without any awareness that another window was opening somewhere else in the galaxy at nearly the same moment, close enough in time to feel like simultaneity, but separated by millions of years in either direction, far enough that no vessel ever launched between them could have arrived before one of them went dark. This is temporal isolation, not loneliness in any emotional sense. The universe does not traffic in loneliness. It is a structural feature of a cosmos, in which intelligence is brief and space is old, and the gap between any two instances of mind is measured in units of time that dwarf anything biology has words for. The windows open, the windows close, and the galaxy turns, as it has always turned, carrying its cargo of burning stars and cooling worlds and brief, improbable sparks of awareness through a darkness that does not notice their passing. But even temporal isolation, devastating as it operates within a universe that is at least geometrically stable. The distances are vast but fixed. The windows are brief but real. The barriers of distance, energy, and time are formidable, but they share a common character. They make contact extraordinarily difficult. They make it improbable to the point of near impossibility. They do not make it physically impossible. For that, the universe has reserved one final barrier, one that operates not at the scale of a galaxy or a civilizational lifespan, but at the scale of the cosmos itself, one that does not merely raise the cost of contact or compress the window of opportunity, one that removes the opportunity entirely permanently for the overwhelming majority of the universe, and does so through a mechanism so elegant and so absolute that no engineering can address it. The universe is not standing still, and the speed at which it moves away from itself has consequences that will seal the fate of every civilization that has ever existed or will ever exist on a timeline that has already begun. Not all stars are equal. This is a statement so obvious that it risks being dismissed before its implications are fully examined. The night sky makes the inequality visible even to the naked eye. Some stars burn white and fierce, others glow a soft amber, some pulse, some drift in pairs. The diversity of stellar types visible from a dark field on a clear night hints at a deeper diversity of timescales, energy outputs, and habitable windows that turns out to be among the most consequential facts in the question of interstellar contact. A star is at its core a negotiation between two forces. Gravity pulls inward, compressing the stellar material toward the center with a force proportional to the total mass involved. Thermal pressure pushes outward, generated by the nuclear fusion reactions igniting in the core when temperatures and pressures climb high enough to force hydrogen nuclei together into helium. The star exists in equilibrium between these two forces for as long as it has hydrogen to burn. When the hydrogen runs out, the negotiation ends. The star changes, sometimes dramatically. The critical variable is mass. Mass determines everything. It sets the core temperature, it sets the fusion rate, it sets the luminosity, and most importantly for the question of civilizational contact, it sets the lifespan. The relationship between mass and lifespan is not linear. It is steep and inverse, in a way that produces radically different outcomes across the range of stellar masses observed in the galaxy. A star like the Sun, a G-type main sequence star with a mass of approximately 1 solar mass, burns steadily for roughly 10 billion years. It is currently 4.6 billion years into that lifespan, with approximately 5.4 billion years remaining before it exhausts its core hydrogen and begins its evolution into a red giant. But the habitable window for planets orbiting the Sun is shorter than the stellar lifespan. As a star ages on the main sequence, it gradually brightens. The Sun is approximately 30% more luminous today than it was when the solar system formed. This slow brightening has a consequence for habitability. Within roughly 1 billion years, the Sun's increasing output will push Earth beyond the inner edge of the habitable zone, triggering a runaway greenhouse effect that will boil the oceans and sterilize the surface. The habitable window for Earth is therefore not 10 billion years. It is closer to 5 or 6 billion years, total of which approximately 4.6 billion have already passed. Perhaps 1 billion years remain before conditions become untenable for complex surface life. 1 billion years sounds vast. Against the backdrop of what follows it, we'll begin to feel modest. Now consider a star somewhat more massive than the Sun. An F-type star with a mass of roughly 1.3 solar masses burns hotter and bluer, pouring out significantly more energy per second than a Sun-like star. The increased fusion rate exhausts the hydrogen supply faster. The total main sequence lifespan of an F-type star runs approximately 4 to 5 billion years. If intelligence requires something approaching the 4 billion years of prior biological evolution that it took on Earth, F-type stars are marginal. Their clocks run faster than the evolutionary process can comfortably accommodate. The habitable zone shifts outward more rapidly as the star brightens and the window for stable planetary climates may close before the biological complexity required for intelligence has had time to assemble. Some F-type stars may host civilizations. The uncertainty in the timescales of biological and cognitive evolution is large enough that confident exclusion is unwarranted. But F-type stars are less promising than Sun-like stars, and their habitable windows are correspondingly shorter. Move upward in mass to A-type stars, roughly twice the solar mass, and the picture darkens considerably. These stars burn through their hydrogen in under 2 billion years. Their habitable zones shift so rapidly during the early main sequence that planetary climates may never stabilize long enough for complex multicellular life to emerge. Whatever worlds orbit A-type stars experience conditions that change faster than evolution can track. The biosphere, if it begins at all, finds itself perpetually racing against a clock it cannot win. These stars are luminous and beautiful. They dominate the night sky with their blue-white brilliance precisely because their enormous energy output makes them visible across vast distances. Sirius, the brightest star in the night sky, as seen from Earth, is an A-type star approximately 8.6 light-years away. Vega, the fifth brightest, is A-type and lies 25 light-years distant. These are stellar neighbors on galactic scales, and yet neither is a credible host for a technological civilization. They simply do not burn long enough for the slow machinery of biological evolution to complete its work. Above A-type stars, the situation becomes irrelevant to the question of life entirely. B-type and O-type stars The most massive stellar objects in the galaxy exhaust their fuel in tens of millions of years. They die in spectacular supernovae before any multicellular organism could evolve in their vicinity. They are engines of chemical enrichment. Their deaths seed the interstellar medium with heavy elements that will eventually find their way into the next generation of stars and planets, but they are not homes. They burn too fast and too violently for life to establish itself around them. At the opposite end of the mass spectrum, the picture becomes more complicated. Red dwarf stars, M-type stars with masses ranging from roughly 0.08 to 0.6. Solar masses are by far the most numerous stellar type in the galaxy. They constitute approximately 70 to 75% of all stars in the Milky Way. A red dwarf of 0.1 solar masses burns so frugally with core temperatures and fusion rates, so much lower than a sun-like star, that its total main sequence lifespan stretches to approximately 10 trillion years. 10 trillion. The current age of the universe is 13.8 billion years. A red dwarf of this mass will still be burning steadily when the universe is nearly 1,000 times its current age. In terms of raw, temporal availability, red dwarfs offer something that no other stellar type can match, essentially unlimited time. If biological and cognitive evolution requires only the right conditions sustained for long enough, red dwarfs should be the galaxy's premier incubators of intelligence. And yet the case against them is significant. The habitable zones of red dwarfs lie extremely close to the star. A planet orbiting within the habitable zone of a star, with 1/10 of the solar mass, sits at roughly 1/20th of Earth's orbital distance. At such proximity, the gravitational influence of the star is intense. Tidal forces act on the planet continuously, gradually slowing its rotation until one face permanently points toward the star and the other faces permanently away. This process, called tidal locking, produces a world of permanent noon on one hemisphere and permanent midnight on the other. Whether a tidally locked world can sustain a stable, life-supporting climate remains one of the genuinely open questions in planetary science. Atmospheric circulation might transport heat from the day side to the night side with sufficient efficiency to prevent the extremes from becoming lethal. Thick atmospheres with high heat capacity might moderate the temperature difference. Planets at the outer edge of the habitable zone might avoid tidal locking entirely, retaining a rotation rate that distributes stellar heating more evenly. These possibilities are real, but they represent optimistic outcomes that may not be typical. The median tidally locked world might present conditions far more hostile than the optimistic scenarios suggest. Red dwarfs also flare. Young red dwarfs in particular produce frequent and violent stellar flares, sudden eruptions of energy that can increase the star's luminosity by factors of hundreds or thousands within minutes. A planet orbiting within the habitable zone of an active young red dwarf endures periodic radiation storms of extraordinary intensity. These storms are not merely uncomfortable. They strip hydrogen from planetary atmospheres at rates that, accumulated over millions of years, can deplete an atmosphere entirely. A planet without an atmosphere cannot maintain liquid surface water. A planet without liquid surface water loses its primary medium for the chemistry of life. Older red dwarfs become calmer. The flaring frequency decreases as the star ages, settling into a more sedate pattern of occasional modest eruptions. But the calming takes billions of years. During the turbulent early phase, the habitable zone is a radiation-drenched environment that may prevent life from establishing itself in the first place. The very longevity of red dwarfs, their defining advantage, is partially negated by the severity of their early behavior. There is also a subtler problem with red dwarf systems that relates directly to the temporal isolation of civilizations. Because red dwarfs have been burning steadily since the early universe, the oldest red dwarf systems are ancient in a way that sun-like stars cannot match. A red dwarf that ignited 10 billion years ago has been providing stable energy to its planets for 10 billion years. If life arose on one of those planets and intelligence followed, the civilization might have achieved technology billions of years ago. Billions, not millions, billions. A civilization that became technological 5 billion years ago, before the solar system even formed, has had 5 billion years to develop, evolve, and change in ways that make the concept of a technological civilization sending radio signals almost certainly obsolete as a description. Such a civilization, if it still exists in any recognizable form, has had time to undergo transformations that dwarf the distance between a bacterium and a human being in terms of the degree of change involved. Whether it would still be detectable, contactable, or interested in physical interaction with newly technological species is a question that resists confident answering. The categories by which we define civilizations, technology, communication, exploration may have no relevance to what such an ancient lineage of intelligence has become. Bringing these stellar considerations together produces a picture of what astrobiologists sometimes call the galactic habitable zone. Not a region defined purely by location within the galaxy, but a region defined by the intersection of stellar-type age metallicity and the proximity of hazardous astrophysical processes. The inner regions of the galaxy close to the densely packed stellar core are subject to elevated rates of supernovae gamma-ray bursts and gravitational disruptions that may sterilize planets on timescales short enough to prevent complex life from emerging. The outermost regions of the galactic disk contain stars with low metallicity, low concentrations of heavy elements, because the process of stellar nucleosynthesis that produces carbon, oxygen, silicon, and iron requires multiple generations of stars to cycle through formation and death, each generation enriching the interstellar medium with heavier elements. The first generation of stars formed from primordial hydrogen and helium almost entirely. Rocky terrestrial planets like Earth require heavier elements. The earliest stars in the galaxy could not produce Earth-like worlds because the raw materials did not yet exist. The galactic habitable zone narrows the field further. Not all regions of the galaxy have been capable of hosting complex life for the same duration. The habitable band favors intermediate galactic radii, far enough from the violent core to avoid the most intense radiation environments, close enough to the regions of active star formation and chemical enrichment to have access to the heavy elements required for rocky planet formation. Our solar system sits within this band, at a galactic radius of approximately 26,000 light-years from the center. Even within this habitable band, the age distribution of stars creates a temporal patchwork. Stars formed during different epochs of galactic history carry different chemical compositions, reflecting the enrichment state of the interstellar medium at the time of their formation. Earlier stars tend to have lower metallicity, which means their planetary systems, if they formed at all, contain less raw material for rocky worlds. Later, stars form with higher metallicity and are more likely to host terrestrial planets of the type that might support complex life. This patchwork means that the galaxy is not uniformly ripe for life across its entire history. Certain epochs were more productive than others. Certain stellar populations formed at certain times in certain regions were better positioned to produce habitable worlds than others. The distribution of actually habitable worlds across galactic time is uneven in ways that create additional temporal isolation between civilizations. A civilization arising around a star formed 10 billion years ago in the outer galactic disk, a star of somewhat lower metallicity, orbited by planets with less heavy element content than Earth, might have developed under conditions subtly, but importantly different from those that produced human intelligence. The biological toolkit available to evolution on such a world might have been constrained in ways that altered the trajectory toward complexity. Or it might have proceeded identically. The uncertainty is genuine. What is not uncertain is that such a civilization's temporal window is offset from ours by 10 billion years. If it lasted 1 million years, it ended 9 billion years ago. 9 billion years before the formation of our solar system. At the moment that civilization ceased, the atoms that would eventually become the sun were distributed across the interstellar medium as diffuse gas not yet gathered into the molecular cloud that would collapse to form our star and its planets. The civilization burned and ended in a universe that did not yet contain us in any form whatsoever. There is something profoundly isolating about this asymmetry. Not just that the civilization is gone, but that it was gone before we began, before any molecule in our bodies was assembled, before any ancestor of any organism on Earth existed. The separation is not merely temporal in the sense that they lived in a different era. It is temporal in the sense that their entire existence preceded ours so completely that the word simultaneous has no meaning applied to them and us. They might as well have existed in a different universe for all the interaction possible between us. Combine the stellar lifespan problem with the civilizational lifespan problem and the spatial distribution problem, and the compound isolation becomes overwhelming. Two civilizations must arise around stars whose habitable windows overlap. Those stars must be close enough in space for travel to be feasible. The civilizations must themselves overlap temporally within those overlapping habitable windows. The overlap must be long enough for a journey to be completed in one direction, and the information about the destination's existence must travel at the speed of light before the journey can even begin. Calculate the probability of all these conditions being met simultaneously using realistic distributions of stellar types, formation epochs, civilizational lifespans, and the energy constraints on travel speed. The result is not zero. Physics does not produce exact zeros when dealing with probabilistic questions about large numbers, but the result is small enough that across the galaxy's entire 13 billion year history, the number of successful physical contacts between independently arising civilizations might be countable on the fingers of one hand. Might be zero. The stars are not merely lamps scattered across the dark to illuminate the void. They are clocks. Each type ticks at a different rate. Each one defines a window of warmth and stability within which the slow work of evolution can proceed. And when the clock runs out, the window closes. Whatever was inside it is gone, not merely distant, gone, removed from the set of things that can be visited, contacted, or known by any civilization arising after the window closes. The galaxy is full of closed windows, ancient stars that burned before complex chemistry existed anywhere in the cosmos, intermediate stars that warmed their worlds for a few billion years and then swelled and consumed them. Dim stars still burning today, but perhaps too turbulent or too tidally constraining for life to have gained a foothold. The fraction of all windows that are open simultaneously in the right locations with the right conditions during the right epochs is small, very small. And yet here we are, behind one of those windows, burning briefly in the dark, looking out at a galaxy full of closed shutters and wondering what burned behind them before they closed. The temporal patchwork of stellar lifespans adds one final layer to the architecture of isolation that has been assembling across the preceding discussion. Distance isolates civilizations in space. The speed limit isolates them in velocity. The energy abyss isolates them in resources. The brevity of civilizational windows isolates them in time. And stellar lifespans isolate them in the deep temporal structure of the galaxy itself, in the epochs of formation and death that ensure most civilizations were separated not merely by light years, but by billions of years of history that neither can access. Each layer of isolation is independent. Each arises from different physics, and each one catches whatever slips through the layer before it forming a nested series of barriers whose combined strength exceeds anything a single civilizational lifetime can hope to overcome. But even this, the full weight of spatial distance, relativistic speed limits, energy, impossibilities, temporal mismatch, and stellar deadline, describes a universe in which the barriers are formidable but theoretically navigable under some combination of extreme longevity and extreme engineering. A civilization that persists for 1 billion years, that achieves Kardashev Type 2 energy mastery, that solves the biological and mechanical challenges of multi-generational interstellar travel. Such a civilization might in principle thread the needle of overlapping temporal and spatial windows and make contact with a neighbor. In principle, because the universe has one more barrier in reserve, the final one, the one that does not make contact difficult or improbable or energetically ruinous, the one that makes it for most of the universe geometrically impossible, not as a consequence of anything that could be engineered around, not as a consequence of any civilizational limitation, as a consequence of the universe itself expanding faster than anything inside it can move. Isu Arlu. Claude responded. In 1929, an astronomer at the Mount Wilson Observatory in the mountains above Los Angeles published a short paper that changed the size of the universe. In 1929, an astronomer at the Mount Wilson Observatory in the mountains above Los Angeles published a short paper that changed the size of the universe. Edwin Hubble had spent years photographing distant galaxies, or nebulae, as they were still called, their true nature, as separate stellar systems comparable to the Milky Way only recently established. He had been measuring their velocities by analyzing the shift in their light spectra. When an object moves away from an observer, the light it emits stretches to longer redder wavelengths, a phenomenon called redshift, analogous to the way a receding ambulance siren drops in pitch as it moves away. When an object approaches, the light compresses to shorter, bluer wavelengths. The degree of shift encodes the velocity of the source with precision that spectroscopic instruments could measure to considerable accuracy. What Hubble found when he compiled his measurements and plotted them against the estimated distances to each galaxy was a relationship so clean and so unexpected that its implications took years for the scientific community to fully absorb. Every galaxy beyond the local group was receding. Not some of them, not most of them, every one. And the velocity of recession was not random. It was proportional to distance. A galaxy twice as far away receded twice as fast. 3 times the distance, 3 times the recession velocity. The relationship was linear, described by a single constant, now called the Hubble constant, that converted distance directly into recession speed. The universe was expanding. Not expanding in the sense of galaxies flying outward through a pre-existing void like fragments of an explosion moving through empty space. Expanding in a more fundamental and more disorienting sense. The space between galaxies was itself growing. The fabric of the cosmos was stretching, carrying galaxies along, as passive passengers, increasing the distances between them, not because the galaxies were moving through space, but because space itself was accumulating between them. The distinction is not merely semantic, it is physically precise, and its consequences are absolute. Georges Lemaitre, a Belgian physicist and Catholic priest who had derived the expanding universe solution from Einstein's equations of general relativity 2 years before Hubble's observational confirmation, understood immediately what the expansion implied when run backward in time. If the universe is expanding now, it was smaller in the past. Smaller still further back, arbitrarily small at some finite moment in the past. The universe had a beginning, a specific, calculable moment from which all of space and time and matter and energy emerged. Lemaitre called it the hypothesis of the primeval atom. Others initially dismissively called it the Big Bang. The name stuck. The Big Bang occurred approximately 13.8 billion years ago. Since that moment, space has been expanding continuously. The expansion has not been constant. In the universe's earliest moments, it was extraordinary, an episode of exponential inflation during the first fractions of a second that stretched the cosmos by factors so large they resist description. After inflation, the expansion continued, but decelerated, slowed by the mutual gravitational attraction of all the matter in the universe. For most of cosmic history, the expansion was expected to continue decelerating, eventually halting perhaps, or slowing to some asymptotic crawl. In 1998, this expectation was overturned by one of the most startling observational discoveries in the history of science. 2 independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, were using distant Type Ia supernovae as standard candles to measure the expansion rate of the universe across cosmic time. Type Ia supernovae are produced when a white dwarf star in a binary system accretes matter from its companion until it exceeds a critical mass threshold and detonates in a thermonuclear explosion of remarkably consistent brightness. Because their peak luminosity is well calibrated, they can be used as cosmic distance markers. Measuring how bright they appear tells you how far away they are, and measuring their redshift tells you how fast they are receding. Both teams expected to find evidence that the expansion was decelerating. Gravity, acting on all the matter in the universe simultaneously, should be gradually applying the brakes. What they found instead was the opposite. The most distant supernovae were fainter than expected, farther away than they should have been, if the expansion were decelerating. The universe was not slowing down. It was speeding up. The expansion was accelerating. Something was pushing the universe apart faster, with every passing era. Something with a repulsive gravitational effect, distributed uniformly throughout all of space and powerful enough to overcome the attractive gravity of all the matter in the observable universe. This something was given the name dark energy. Its nature remains one of the deepest unsolved problems in physics. It may be a property of space itself, an intrinsic energy density of the vacuum that does not dilute as space expands. It may be a dynamical field that evolves over time. It may require physics beyond anything currently in the standard model to explain. What is known is its effect. Dark energy constitutes approximately 68% of the total energy content of the universe. It permeates all of space with a density that remains constant per unit volume as the cosmos expands. Normal matter and radiation thin out. As the universe grows, their fixed quantities spread across increasing volume, reducing their density. Dark energy does not thin out. Its density per unit volume stays constant, which means that as expansion creates new space, new dark energy fills it automatically. The more space exists, the more dark energy exists. The more dark energy exists, the stronger the repulsive effect. The stronger the repulsive effect, the faster space expands. The faster space expands, the more new space is created. The cycle feeds itself without limit. The expansion does not merely continue, it accelerates, and the acceleration itself accelerates, compounding across cosmic time in a progression that has consequences for the accessibility of the universe that go far beyond anything the barriers discussed earlier imposed. The consequence that matters most for civilizational contact is this: the cosmic event horizon is shrinking. This requires careful distinction. The observable universe, the sphere of space from which light has had time to reach Earth since the cosmos became transparent, is still growing. Ancient light from the most distant objects continues to arrive, having been traveling toward us since shortly after the Big Bang. Objects that were once too far away for their early light to have reached us yet are gradually entering our observable volume as that light completes its journey. The observable universe grows at the speed of light, but the event horizon, the boundary beyond which events occurring right now at this moment will never be observable to us, is a different concept entirely. It is defined not by where the ancient light came from, but by where a signal emitted today could eventually reach us, given the accelerating expansion. Because expansion is accelerating, there is a finite distance beyond which a signal emitted today will never reach us. The expansion will carry the source faster than the signal can travel, and the gap will grow rather than shrink. That boundary currently lies at approximately 16 billion light-years. Any galaxy currently beyond this distance is receding so fast that no signal it emits today will ever reach the Milky Way. The signal moves toward us at the speed of light through local space, but the space between the source and us expands faster than the signal traverses it. The signal falls behind like a swimmer stroking against a current stronger than any stroke can overcome. This is not a faint signal problem. There is no amplifier that could help. The signal is moving at the maximum speed permitted by physics. The expansion of space is not constrained by the same limit. Space expands at whatever rate the energy content of the universe dictates, and currently that rate exceeds the speed of light at distances beyond the event horizon. The separation between the source and us grows at faster than light speed, not because anything moves through space at that velocity, but because the intervening space itself accumulates faster than light can traverse it. General relativity permits this. Special relativity's speed limit applies to objects moving through space, not to the expansion of space itself. The galaxies beyond the event horizon are not moving through space at superluminal velocities. They are approximately stationary within their local regions of space. But the space between them and us is growing at a rate that separates us faster than light can close the gap. Now examine what this means for the observable universe and the civilizations within it. The observable universe currently spans approximately 93 billion light-years in diameter. This number exceeds the age of the universe, multiplied by twice the speed of light, because space has been expanding throughout the entire journey time of the light we observe. Objects at the edge of the observable universe were much closer when they emitted the light we detect today. That light has been traveling for nearly 13.8 billion years, but the objects that emitted it have since been carried by expansion to distances far exceeding what simple light travel time would suggest. Within this observable sphere sit approximately 2 trillion galaxies, each containing hundreds of billions of stars. The total stellar population of the observable universe exceeds any number for which human language has a comfortable name. And yet, of all these galaxies, of all these potential homes for civilizations, the overwhelming majority are already beyond any possibility of physical contact. The recession velocity of a galaxy increases with distance according to Hubble's law. At a distance of approximately 14 billion light-years, the Hubble radius, the recession velocity equals the speed of light. Beyond this distance, galaxies recede faster than light. A vessel launched from Earth today at any speed up to and including the speed of light would never reach a galaxy currently beyond the Hubble radius. The space to be crossed expands faster than the vessel moves through it. The destination recedes forever. Currently, approximately 97% of the galaxies within the observable universe are receding faster than the speed of light. We can see them because their light began its journey when they were closer before expansion carried them beyond the Hubble radius. We are looking at their past. Their present is already unreachable. Their future belongs to a realm we can never touch. Every photograph of the deep universe is a portrait of objects we can observe but never visit. The Hubble Ultra Deep Field Image, one of the most famous astronomical photographs ever taken, shows approximately 10,000 galaxies in a patch of sky smaller than a grain of sand held at arm's length. Nearly every galaxy in that image is already beyond physical reach. We see them, we can study them, we can never go there. The expanding universe has placed an impenetrable wall between us and them, a wall that grows thicker with every passing second and will never be breached. Walk through the scales of distance and observe what expansion does to the possibility of contact at each level. At 50 million light-years, roughly the distance to the Virgo cluster, the nearest major concentration of galaxies beyond the local group, the recession velocity is approximately 3,500 kilometers per second. This is significant, roughly 1% of the speed of light, but modest compared to the speed of any conceivable relativistic vessel. A vessel traveling at 10% of light speed can still outrun the expansion at this distance. The journey takes 500 million years. During those 500 million years, expansion increases the distance to the Virgo cluster by several percent. The vessel must cover slightly more ground than the naive calculation suggests, because the destination recedes while the journey is underway. But the recession velocity is far below the vessel's travel speed. The vessel gains ground with every passing moment. It arrives. This is the optimistic regime, distances at which travel is physically possible, if not remotely practical, given the energy requirements and timescales involved. At 500 million light-years, the recession velocity climbs to approximately 1,000 kilometers per second, roughly 3.7% of the speed of light. A vessel traveling at 10% of light speed still gains ground, but more slowly. The effective closing speed is reduced to about 6.3% of light speed after accounting for the expansion of intervening space. The journey time extends significantly beyond the simple distance divided by velocity calculation. But arrival is still theoretically possible. At 2 billion light-years, the recession velocity approaches 14% of the speed of light. A vessel must travel faster than 14% of light speed merely to avoid falling further behind. At exactly 14% of c, the vessel holds its position relative to the expanding background. The destination neither approaches nor recedes. Progress is zero. The vessel must travel substantially faster than 14% of light speed to make any headway at all, and the energy required to reach and sustain these velocities places the mission squarely in the regime of stellar-scale energy budgets. The same regime already shown to be essentially inaccessible to any civilization operating within known physics. At 5 billion light-years, the recession velocity reaches approximately 36% of the speed of light. Any vessel slower than 36% of c falls behind with every passing second. It does not merely fail to arrive. It moves in the right direction while the destination moves away faster. The gap grows, not slowly, at a rate determined by the difference between the vessel's speed and the recession velocity, which widens with time as expansion accelerates. The vessel travels for 1 billion years and arrives further from its destination than when it started. At the current Hubble radius of approximately 14 billion light-years, the recession velocity equals the speed of light. A photon emitted from Earth today in the direction of a galaxy at this distance will never arrive. It moves forward through local space at the maximum permitted velocity, while the total distance to the destination grows at exactly the same rate. The photon makes no progress. It is frozen at the same physical separation forever, not in the sense of being motionless, but in the sense that the ground it covers is immediately replaced by new ground generated by expansion. Beyond this distance, the verdict is absolute and permanent. Nothing we launch today at any velocity will ever arrive. No signal we emit will ever be received. The expanding universe has sealed off the overwhelming majority of the observable volume from any possibility of physical or informational contact. And the situation worsens over time. Because expansion is accelerating, the event horizon is not a fixed boundary, it is a shrinking one. Galaxies that are currently marginally reachable just inside the event horizon will be carried beyond it as expansion accelerates. The set of locations we can reach by launching a vessel today is larger than the set we will be able to reach by launching a vessel in 1 billion years, which is larger than the set reachable in 10 billion years. The window of cosmic accessibility is closing, not metaphorically, literally. The number of galaxies we could in principle reach with a vessel launched at the speed of light decreases with every passing era. Future astronomers in the Milky Way will inhabit a universe with a smaller accessible volume than present astronomers. Their distant descendants will inhabit a smaller universe still, eventually on timescales measured in hundreds of billions of years. Every galaxy outside the local group will have been carried beyond the event horizon permanently. The Virgo cluster, currently 54 million light-years away, will cross the event horizon within approximately 100 billion years. The Coma cluster, roughly 320 million light-years distant, crosses sooner. The great filaments and walls of the cosmic web, the largest structures in the observable universe, will dissolve from our causal volume over similar timescales. Within approximately 150 billion years, every galaxy outside the local group will have passed permanently beyond our cosmic event horizon. The merged remnant of the Milky Way and Andromeda, a collision that will begin in approximately 4 billion years and complete over the following billion, will be the only galaxy in the observable universe of future astronomers. Surrounding it will be perfect, featureless darkness, extending to infinity in every direction. Future observers in that merged galaxy will have no evidence that other galaxies ever existed. The cosmic microwave background radiation, the oldest light in the universe, the afterglow of the Big Bang itself, will have redshifted to wavelengths so long that no conceivable instrument could detect it. There will be no fossil evidence of the Big Bang, no observational trace of the 2 trillion galaxies that filled the early universe. No way to reconstruct from first principles the cosmological framework we take for granted today. They will inhabit a universe that appears to all available evidence to consist of a single galaxy floating in a static eternal void. They will have no way of knowing otherwise. The universe will have hidden its own history behind an expanding wall of geometrical inaccessibility. This is not a distant hypothetical. The process is already underway. The 97% of observable galaxies already receding faster than light are already in this condition. We can see them. We cannot reach them. We cannot send them anything. They cannot send us anything that will arrive. The wall already exists for the overwhelming majority of the universe. What remains are the details of the timeline on which the remaining accessible fraction is sealed off. For civilizations in separate gravitationally unbound galaxy groups, the verdict has already been rendered by physics. A civilization in a galaxy receding from us at faster than the speed of light is permanently beyond reach. No vessel, no signal, no force of any kind can bridge the gap. Whatever intelligence burns there, however ancient, however brilliant, however desperate for contact, is as separated from us as if it existed in a different universe with different physical constants. The space between us does not permit passage. It never will. This is expansion's gift to isolation. The other barriers, distance, speed limits, energy costs, temporal mismatch, stellar deadlines make contact extraordinarily difficult and improbable. Expansion makes it, for the overwhelming majority of the universe, physically impossible. Not difficult, not improbable, impossible. A categorical impossibility arising from the geometry of space-time under accelerating expansion with no engineering solution, no theoretical workaround, and no exception for civilizations sufficiently advanced to wish it were otherwise. Physics does not grant exceptions based on desire. Within the Milky Way itself, expansion does not dominate. The galaxy is gravitationally bound. The distances between stars measured in thousands of light years are not growing due to cosmic expansion. The barriers within our galaxy remain those discussed earlier: the speed limit, the energy abyss, the brevity of civilizational windows, the finite lifespans of stars. These barriers are formidable, but they do not carry the absolute character of expansion's verdict on intergalactic contact. But expansion eliminates any possibility of rescue assistance or augmentation from beyond the local group. If the solution to the contact problem lies in a civilization 100 million light-years away, a civilization that has solved the energy barriers, that has mastered relativistic propulsion, that has developed the technology to reach across interstellar distances within its own galaxy, it cannot help to us. The expanding universe ensures that its capabilities, however extraordinary, are locked behind a wall it cannot cross and we cannot open. The universe creates. The universe isolates. The same expansion that cooled the primordial plasma into atoms, allowing chemistry to begin, also carries the products of that chemistry away from each other at velocities no physics permits anything to match. Creation and isolation emerge from the same equations. The Big Bang produced everything that exists, including the expansion that ensures most of what exists will never interact with most of the rest. Now the full architecture of the prison is visible. 6 walls, each arising from different physics, each independent of the others, each sufficient on its own to make interstellar contact extraordinarily difficult, and together forming a structure whose combined strength exceeds the sum of its parts by a margin that resists any optimistic accounting. The distances between civilizations imposed by the geometry of a galaxy containing 400 billion stars spread across 1,000,000 light-years of space. The speed of light, absolute and unyielding, a structural property of space-time itself, confirmed by every particle accelerator and atomic clock ever built. The energy abyss, the exponential scaling of propulsion requirements that demands stellar-scale energy inputs for any velocity, making the journey meaningful. The brevity of civilizational windows, the 1 in thousands probability that any 2 civilizations exist simultaneously and within range of each other. The finite lifespans of stars, the temporal patchwork of opening and closing habitable windows across billions of years of galactic history. And expansion, the accelerating growth of space itself, the shrinking event horizon, the permanent and irrevocable sealing off of 97% of the observable universe from any possibility of contact. 6 walls, nested inside each other, each one catching what slips through the one before it. The universe was not built for meetings. Stand back from everything that has been built across this journey. Not to summarize it, the details deserve to remain sharp, not dissolved into generality, but to see its shape, to observe what 6 independent barriers arising from 6 different branches of physics look like when assembled into a single structure. The shape is not a wall. A wall has a single surface, a single point of failure, a single place where a sufficiently determined effort might find a crack. What the universe has constructed is something more complete than a wall. It is a series of nested chambers, each one enclosing the last, each one built from different materials, each one requiring a different kind of impossibility to breach. You escape the first chamber and find yourself inside the second. You escape the second and the third closes around you. The chambers do not weaken each other, they reinforce each other, each one catching whatever the one before it failed to stop. The first chamber is distance, 400 billion stars spread across 100,000 light-years of disk. Civilizations, even if numerous, scattered through a volume so vast that the nearest neighbor sits thousands of light-years away under any realistic assumption. The distances are not metaphors for separation. They are physical realities measured in the time light requires to cross them, and light requires millennia. The second chamber is the speed limit. The structural ceiling of space-time itself confirmed to more decimal places than any other physical law, embedded so deeply in the architecture of reality that overturning it would require dismantling electromagnetism, particle physics, and cosmology simultaneously. Nothing with mass reaches it. Approaching it demands energy that scales toward infinity. It is not a record, it is a boundary condition of the universe's geometry. The third chamber is the energy abyss, the exponential scaling of propulsion requirements as velocity increases, the rocket equations compounding demand for fuel masses that exceed planets at relativistic speeds, the impossibility of manufacturing antimatter in useful quantities, the geometric collapse of laser sail concepts under payload scaling, the requirement of exotic matter for warp solutions that may not exist anywhere in nature. Not one obstacle, but a family of obstacles, each arising from different physics, each pointing toward the same conclusion. Fast travel costs more than any civilization can reasonably afford, and the cost grows faster than any conceivable economy can scale. The fourth chamber is temporal isolation, the 1 in thousands probability that any two civilizations exist simultaneously within the galaxy's 13-billion-year history. The survival requirement placed on destination civilizations by journey times measured in millennia. The signal problem, the fact that all information about a destination is old by exactly the light travel time when received. The arrival scenarios that end in graveyard planets, thriving biospheres with extinct tenants, living worlds whose intelligence burned and faded tens of thousands of years before the vessel completed its crossing. The universe creates civilizations in sequence, not in synchrony, and the sequence is long enough that most of its chapters never share a page. The fifth chamber is stellar time, the patchwork of habitable windows imposed by the diversity of stellar types and formation epochs, the F-type stars that burn too fast for evolution to complete its work, the A-type stars that exhaust their fuel before multicellular organisms emerge, the red dwarfs that offer unlimited time but perhaps hostile tidal and radiation environments, the ancient civilizations that might have arisen around long-lived stars billions of years ago and ended before our sun ignited their worlds, now orbiting stellar remnants that retain no trace of what once happened there. The galaxy is not uniformly available across time. It is a patchwork of openings and closings, most of which do not overlap with ours. The sixth chamber is expansion, the accelerating growth of space itself, the cosmic event horizon that currently places 97% of observable galaxies beyond any physical reach, the shrinking accessible volume that makes the universe progressively less navigable with every passing era, the permanent and irrevocable sealing of most of the cosmos behind a geometric wall that no engineering addresses, no velocity overcomes, and no future physics will circumvent, because the wall is not made of matter or energy, but of the rate at which space itself accumulates. 6 chambers, each one independent, each one arising from different equations. Together, they form a prison whose total strength has never been fully assembled in one place and examined for what it actually means. It means this: the universe almost certainly contains other minds. The numbers are too large, the chemistry too universal, the conditions too widespread for Earth to be the only world where molecules learn to think. Somewhere across the 2 trillion galaxies and the hundreds of billions of stars within each one, the same processes that produced awareness here have almost certainly produced it elsewhere. Perhaps many elsewheres. Perhaps billions of elsewheres distributed across the galaxy's long history, each one a brief burning of curiosity in the dark, and virtually none of them will ever know about the others. Not because they failed to look, not because they lacked the intelligence or the will or the instruments, but because the architecture of the cosmos ensures that existence and accessibility are two entirely different propositions. The universe creates intelligence with one hand and isolates it with the other, using the same physics for both operations, the same constants, the same equations. The relativity that governs the nuclear reactions powering stars also imposes the speed limit that makes crossing the distances between them so expensive as to be essentially impossible at any velocity that matters. The gravity that pulls gas into stellar nurseries also determines that galaxies spread across millions of light-years of void. The dark energy that accelerates expansion also ensures that most of the universe is permanently beyond reach. Creation and isolation are not competing forces in the cosmos. They are consequences of the same underlying structure. This is the resolution the universe offers to the Fermi paradox. Not that intelligence is rare, not that civilizations destroy themselves, not that they are hiding or transcending or deliberately silent, but that the architecture of physical law ensures that even abundant intelligence remains profoundly structurally permanently separated from other instances of itself. The silence is not absence, it is geometry. There is a temptation at this point in the argument to receive this as tragedy, to feel the weight of it pressing down the knowledge that, however many minds have gazed at alien skies and wondered they wondered alone, that the vessels were never launched and never arrived, or arrived to find only silence and the slowly weathering evidence of something that used to be, that the great conversation of the cosmos, the exchange of knowledge and perspective between independently arising intelligences, has almost certainly never occurred and almost certainly never will. This feeling is honest. It deserves acknowledgement before it is reframed, but consider what the universe has actually accomplished, stripped of the longing for what it has not provided. From an initial state of unimaginable density and temperature, from a moment before which the word before has no meaning, the cosmos expanded and cooled and organized itself across 13.8 billion years into structures of staggering complexity. It built protons from quarks. It built atoms from protons and electrons. It built molecules from atoms. It built stars from hydrogen and forged heavy elements in their cores. It scattered those elements across light years in supernovae and gathered them into new stars with rocky planets and liquid oceans. It stirred those oceans with energy from above and below and waited with the patience that only a universe operating on billion-year timescales can muster for chemistry to find its way toward biology. And on at least one world and almost certainly on others distributed across the galaxy's long history, it worked. The chemistry became biology. The biology became complexity. The complexity became awareness. The universe produced matter that can contemplate itself, atoms that can wonder about atoms, hydrogen that has spent 13.8 billion years becoming something capable of understanding where it came from and what surrounds it. That is not a small thing. That is measured against the background of a cosmos that is mostly vacuum and mostly darkness and mostly temperatures near absolute zero, an extraordinary thing. A thing so improbable in its details and so consequential in its implications that its existence on even one world represents something the universe spent nearly 14 billion years building toward. You are that thing. Not you in the sense of your individual biography or your particular configuration of memories and preferences. You in the sense of the capacity you carry, the capacity to measure the distance to stars, to derive the age of the universe, to calculate the probability that you are alone, to feel the weight of that calculation and to continue anyway. To look at a cosmos that has constructed every possible barrier to your knowing it fully, and to know it as well as those barriers permit. This capacity is what the universe spent 13.8 billion years assembling. It is not incidental to the story. It is the story. The isolation is real. The walls are real. But consider what the reaching means precisely because the walls are real. Every equation derived about the behavior of light traveling between galaxies is a civilization pressing its hands against the glass of its enclosure and mapping with extraordinary precision the shape of the space beyond it. Every observation recorded of the cosmic microwave background, the oldest light in the universe, the faint afterglow of the moment space became transparent, is a mind 13.8 billion years removed from that moment, reconstructing what happened there from the evidence left, in a pattern of temperature fluctuations measured to parts per million. Every particle accelerator that confirms the predictions of special relativity to 12 decimal places is a species discovering through careful measurement and the discipline of testing the exact nature of the wall that surrounds it. The walls are real, the knowledge of them is also real, and the knowledge does not diminish the enclosure. It is the most extraordinary thing the enclosure contains. There is a particular kind of wonder that belongs specifically to understanding limits, not the wonder of open horizons of endless possibility, of a universe that yields freely to curiosity, but the harder, deeper wonder of a universe that resists, that imposes genuine constraints, that says no in the language of mathematics, and the realization that you are the kind of thing capable of hearing that no and understanding exactly what it means. A universe without limits would be a universe without structure. A universe without structure would be a universe without stars, without chemistry, without the long, patient work of evolution. The limits are not flaws in the design, they are the design. The same constraints that isolate civilizations from each other also create the stable, lawful, comprehensible universe in which civilizations can exist at all. The speed of light is a wall. It is also the mechanism by which information propagates through space, the foundation of causality, the constant that makes the universe's behavior consistent across time and location. Without it, or with a different value for it, the electromagnetic force would operate differently, atomic structure would change, chemistry would change, and the particular configuration of carbon chemistry that produces biology would be unavailable. The wall is load-bearing. Remove it, and the room it encloses collapses. The vast distances between stars are a barrier to contact. They are also the reason each stellar system is gravitationally stable across the billions of years that complex life requires. If stars were packed closely enough for interstellar travel to be practical on human timescales, their gravitational interactions would perturb planetary orbits on timescales far too short for stable biospheres to develop. The isolation and the stability are consequences of the same spatial distribution. The prison and the home are the same structure. The accelerating expansion that seals off most of the universe from contact also dilutes the density of matter and radiation to levels at which complex chemistry can operate. In the early universe, when everything was packed into a smaller volume, radiation dominated matter, and temperatures far exceeded anything compatible with molecular bonds. The expansion is what created the cool, dark, thinly populated universe in which stars burn steadily for billions of years, and planets orbit in habitable zones and oceans persist long enough for life to emerge. Isolation is the price of habitability. The cosmos does not offer one without the other. This is not consolation, it is description. The universe is built the way it is built, and the way it is built produces both life and isolation from the same equations at the same time, without any possibility of having one without the other. To wish for a universe without the barriers is to wish for a universe without the life. The physics that separates civilizations is the physics that creates them. Look up tonight if the sky is clear where you are. Every point of light visible to the naked eye is a star within our own galaxy, most of them within a few thousand light-years of Earth. Every one of them is a sun, many of them warm planets. Some of those planets may have oceans. Some of those oceans may have life. Some of that life may across sufficient time and under sufficiently stable conditions have produced minds. The photons arriving at your eyes right now from those stars have traveled for years, for decades, for centuries. They carry information about their sources, the temperature of the stellar surface, the chemical composition of the atmosphere, the motion of the star relative to us. They are in a very real sense messages, not intentional ones, but messages nonetheless. The universe, through the medium of light, is continuously broadcasting the properties of every object within our observable volume to every other location from which those objects are visible. We receive those messages. We decode them with spectrographs and interferometers and photometers of extraordinary sensitivity. We read the temperature and the chemistry and the velocity and the age of objects we will never visit orbiting stars. Our descendants will never reach in a galaxy that will eventually seal itself off from the rest of the cosmos and forget it ever had neighbors. We read them. That is what we have instead of contact. Not the thing itself, not the handshake across the void, not the exchange of knowledge between independently arising intelligences, not the confirmation that curiosity is a property of the universe rather than an accident of one particular world. We do not have the meeting. We have the knowledge that the meeting is impossible, derived from the same physics that tells us what lies on the other side of the barriers we cannot cross. Some civilization somewhere in the galaxy's long history almost certainly reached the same conclusion. They mapped their sky. They measured the distances. They derived the speed limit. They calculated the energy costs. They understood the temporal probabilities. They looked at the expanding universe and grasped what it was doing to the accessible volume of the cosmos. And they arrived at the same place we are arriving now, not at despair, because the knowledge itself is too extraordinary for despair to be the appropriate response, at something quieter and harder to name. Perhaps something like this. The universe is full of stars, full of worlds, full of the same chemistry and the same physical laws that produce the awareness reading these words. It is full of the potential for minds, and across its long history, almost certainly full of actual minds. Distance that does not punish, distance that does not exclude, distance that simply is a natural consequence of a cosmos large enough and old enough and structured precisely enough to produce minds capable of measuring it. Somewhere separated from you by thousands of light years of vacuum and thousands of years of time, another mind may be reaching the same conclusion tonight. Sitting beneath an alien sky surrounded by constellations, you would not recognize understanding for the first time that the universe creates intelligence and then keeps each instance of it in a separate room, not out of cruelty, not out of indifference, out of geometry, out of the deep mathematical structure that makes stars and planets and minds possible in the first place. You will never meet them, they will never meet you, but you share something that no distance can erase and no expansion can carry away. You share the same universe, the same laws built you both, the same stellar furnaces forged the calcium in whatever bones they carry and the iron in your blood. The same Big Bang set the initial conditions for both your existences. The same dark energy that isolates you from each other also gave both of you the time and the space and the stable physical environment in which to exist at all. That is not loneliness. That is belonging to something so vast that no single part of it can see the whole. Every civilization is a window. Every window opens onto the same cosmos. And the cosmos is extraordinary enough to be worth the view even in silence, even alone. Even knowing that the silence is permanent, and the aloneness is structural, and the walls of the enclosure are made of mathematics rather than stone, and will never come down. The universe was not built for meetings. It was built for wonder, and in that, at least in that one strange and improbable and magnificent thing, it has succeeded beyond any measure a small mind on a small world could ever fully grasp. The light is here now, in this galaxy, on this world. In this moment of understanding, it is enough.